Okay, so let's look at picture A, the picture of the male, and it's just really showing you the location of the urinary bladder. Let's see, and then the urethra passes from the bladder. Of course, it's much longer in the male. And then for the female, the urinary bladder is this one. And then here's the urethra, which is a much shorter tube than what it is in the male, in location to the vagina and the rectum, and then of course the male urethra in location and bladder in location to the rectum. So with the female, the uterus is superior to the urinary bladder. So you can see the location of the uterus and the rectum in comparison with the urinary bladder. And then if you look over here in picture C, this is the urinary bladder in the male, and it shows where the ureter connects. Of course, those are the tubes that connect from both ureters would connect here. This is a ligament, sorry. Both ureters would connect here, and they would enter into the bladder. The detrusor muscle, which helps in, when you put pressure on it, it helps in micturition. Then you have the urethra beginning at the prostate gland. Okay, so let's just look at the notes. I'm not asking a lot of questions about the anatomy of the urinary bladder, and I just want you to make sure you know that the urethra in males is also a pathway for semen, and that it is longer in males, of course. The urinary bladder has an area called the trigone, and it's a triangular area. It's at the base of the urinary bladder, and it's formed by the two ureteral openings and the urethral entrance. So if we go back, you can see that. This is the area called the trigone. This is the center of the trigone. And it contains the involuntary internal urethral sphincter that's composed of involuntary smooth muscle. That one must relax in order for you to urinate, or in order for micturition to take place. The bladder wall contains layers of smooth muscle called the detrusor muscle. When you contract that muscle, it expels the contents of the bladder into the urethra. In males, the urethra extends 18 to 20 centimeters to the external opening or external urethral orifice at the tip of the penis. In females, the urethra is very short, 2.5 to 3 centimeters from the bladder to the external urethral orifice near the anterior wall or the front of the vagina. Urination is called micturition. We also call it voiding. There's some information on the voiding reflex, but the checkpoint question, just make sure that you know, okay, these are the things you need to know. Urination is called micturition, and voluntary control of urination depends on your ability to control which muscle. It would be the detrusor muscle. And know the differences, going back to the urethra in males and females, and just know the differences between the males and the females as far as the anatomy of the urethra. There's not going to be a lot. There is a whole section on fluid balance and all that. I'm skipping through a little bit because there's just so much in this chapter. But I want you to be familiar with electrolyte balance. Electrolytes are result when chemicals called salts, which are inorganic chemicals, inorganic compounds, when they dissolve in the water, in the fluid, in your tissue fluid and your blood plasma in your body, and also in the cytosol inside of your cells. So when those salts dissolve, they release ions like sodium and potassium. Sodium and potassium probably are the primary ones. There's calcium, magnesium, and even some ions like polyatomic ions like bicarbonate. But the reason electrolytes are important is because the gain or loss of electrolytes results in the gain or loss of water. Remember how water follows salt, water follows sodium. If we lose sodium, then we're going to lose water. So the concentration of individual electrolytes affects cell function. In addition to affecting water balance, it affects cell functions. We learned in the muscle chapter and the nerve chapter how important sodium and potassium is. Sodium ions and potassium ions are important in nerve impulses, in depolarization and hyperpolarization and repolarization. All of those processes are dependent on sodium and potassium moving across the plasma membrane or the sarcolemma of the muscle fiber, and also the neurolemma, which is the plasma membrane of the nerve of the axon, as well as the cell body and the dendrites. So another is calcium. Calcium plays a role in both of those processes as well. So the most common electrolyte balance problems are caused by an imbalance between sodium gains and losses. Potassium imbalances are less common but much more dangerous. Sodium balance, sodium absorption from the digestive tract and excretion by the kidneys. The rate of uptake varies with the amount of sodium in your diet and the losses by excretion in your urine and your perspiration. We don't tend to have low sodium. Just say that. Sodium tends to be high, but not low, just because, we tend to get plenty of sodium. I say we, like Americans, people from the United States of America tend to get plenty of sodium in their diet, and too much sodium is the problem. So, but potassium is different. We can be low in potassium easily. But the balance of sodium is regulated by aldosterone and ANP. Remember, ANP stands for atrial natriuretic peptide, and they have opposite effects. Aldosterone increases sodium reabsorption into the blood, which, and then water is going to also be reabsorbed because water follows salt. But ANP decreases sodium reabsorption. So it would have the opposite effect. Remember, the overall effect from aldosterone is to raise the blood pressure, but the overall effect from ANP is to lower the blood pressure. Remember the statement, water follows salt, because levels of sodium have a direct effect on water levels. When there's an increase in sodium in your blood, then there's an increase in blood volume, because water follows that sodium into your blood. So you have more water in your blood plasma. That increases the volume, the overall volume of your blood. And when the blood volume increases, the blood pressure increases. For potassium, 98% of the body's potassium is in the intracellular fluid. That means inside the cell, in the cytoplasm, is where we have 98% of the body's potassium, whereas sodium is found in the extracellular fluid. It's high in the ECF. So there's a low potassium concentration in the ECF, or extracellular fluid, which is also can be interstitial fluid or tissue fluid, but it's the fluid outside the cells that surrounds and bathes our cells. There's a balance between the absorption from the digestive tract and excretion by the kidneys, and the rate of loss is affected by aldosterone. Aldosterone doesn't just affect sodium, it also affects potassium, so it increases potassium loss from the kidneys. Problems with potassium balance are less common than problems with sodium, but they're much more dangerous. because problems with potassium can disrupt membrane potentials in excitable tissues like muscle and nerve tissue. Checkpoint question. Question 19. How would eating a meal high in salt content affect the amount of fluid in the intracellular fluid compartment? This would be our tissue fluid. Well, when we eat a meal that's high in salt, that salt gets ends up in our blood. The sodium ions end up in our blood. Water follows that salt into our blood. And even though our urinary system is designed to counteract this, it's still going to cause us to retain fluid. It's going to cause us to, water's going to follow that salt into our intracellular fluid, into our blood plasma, and we're going to retain fluid. And we might even have edema or swelling from that. Now, our urinary system is designed to counteract this, but it can only do so much, Number 20, what effect would being in the desert without water for a day have on the osmotic concentration of your blood plasma? Well, if we're in the desert, we're going to get dehydrated. And when we're dehydrated, it's going to cause our kidneys will eventually, you will end up having a higher amount of ADH. ADH is going to cause water to be retained at the level of the DCT and the collecting duct. It's going to cause water reabsorption back into your blood, so you're going to retain as much fluid as you can, so you end up with a lower volume of more concentrated urine. As far as the osmotic concentration of your blood plasma, it's going to cause you I'm sorry for the hesitation there. I wanted to make sure I was right about this one. Honestly, I felt like I understood what effect it would have on your urine, but I wanted to be sure about what effect it would have on your blood plasma. It's just what you would think. It would increase the osmotic concentration of your blood plasma, and it's going to cause you to sweat more. It's going to cause you you're going to lose fluids when you're in the desert. So you're going to become dehydrated, and therefore the concentration in your blood plasma is going to be higher. Because you have a lower volume of fluid in there. It didn't ask about what would happen with your urinary system, but you should also know that it would cause you to have a higher increase in ADH, and that would cause you to have a lower volume of more concentrated urine. Okay, enough time on that question. Acid-base balance. This is important. I want to spend a little bit of time on this because we do need to understand in the healthcare field, we do need to understand about acidosis and alkalosis. So the normal pH range of the extracellular fluid, and that includes blood plasma, is 7.35 to 7.45. The nervous and cardiovascular systems are most sensitive to a change in pH. Problems with low pH are more common, and that's called acidosis, and they're more common because normal cellular activities generate acids. Like, exercise will generate lactic acid. Normal cellular activities will generate carbonic acid and pyruvic acid or pyruvate. That's generated from glycolysis during cellular respiration, and ketone bodies are generated when especially when your blood glucose levels are high. So what is acidosis? Acidosis is when the pH of your blood plasma or extracellular fluid in general is below 7.35. Severe, which is below 7, can actually be fatal. The central nervous system function declines, leading to coma. Cardiac contractions weaken, leading to heart failure. Peripheral vasodilation drops blood pressure, leading to circulatory collapse, and it is more common than alkalosis. if you've ever heard of acidosis, it's probably in relation to diabetes, particularly a person with type 1, but type 2 can have it too. A person with type 1 or type 2 diabetes can go into diabetic ketoacidosis, or DKA, and that is very, very dangerous, and it can lead to a coma. So that's probably the most common. It's probably, if you've ever heard of it, that's probably where you heard of it. And it's when their blood sugar is high for an extended period of time, for hours. It's very, very high, like in the 400, 500, 600s, just dangerously high. And nothing is done about it. It stays high for a long time. That's when they're going to go into acidosis. Now, alkalosis can happen as well. Dehydration can cause alkalosis. And that's when the pH of the blood is above 7.45. And when it's severe, above 8, it can be fatal. So carbon dioxide and pH. Carbon dioxide levels in your body fluids, when carbon dioxide levels are high, pH is low. What happens is carbon dioxide combines with water, forms carbonic acid, and then breaks up into hydrogen ions and bicarbonate ions. And that increase in hydrogen is what lowers the pH, because the more hydrogen you have, the lower the pH is going to be. So the effect of carbon dioxide is that the rate of breathing can alter blood pH. If you are breathing very, very deep and fast, you're getting rid of carbon dioxide very fast. That means you can raise your blood pH. But if you breathe very shallow, and if you hypoventilate instead of hyperventilate, so you breathe very shallow and slower, then you can actually lower your pH because you are not getting rid of carbon dioxide at the rate that you need to. This is the relationship between carbon dioxide and plasma pH. When the partial pressure of carbon dioxide is between 40 and 45 millimeters of mercury, that's when the blood pH is around 7.3 to 7.45. When the amount or partial pressure of carbon dioxide goes up, blood pH goes down. When the partial pressure of carbon dioxide goes down, blood pH goes up. Now, there are 3 buffer systems in the body. There are protein buffer systems, the carbonic acid bicarbonate buffer system, which is based on this reaction here that I just went over with you, and the phosphate buffer system. These buffer systems are designed to deal with pH changes in your body fluids. So they're designed to donate hydrogen ions when your pH is too high, and absorb or remove hydrogen ions when your pH is too low. For the carbonic acid bicarbonate buffer system, this is the most important buffer system to prevent pH changes caused by metabolic acids like ketones from high blood sugars. The partial pressure of carbon dioxide rises, and what the respiratory does is it excretes carbon dioxide by hyperventilating. The person would breathe very deeply and fast to get rid of as much carbon dioxide as they could. This is something I know personally about. It took me a long time to be able to talk about it, but it's a really good example, so I try to share it with my anatomy students. When my daughter was 2 years old, she went into DKA. She had undiagnosed type 1 diabetes, and we just didn't realize that's what was wrong with her. She had the signs of, excessive urination, and she was drinking lots of fluids, and she just was sick, and we knew she was sick, but we had no idea that she had diabetes. So before she was diagnosed, she went into DKA, which is what led us to rush her to the emergency room. But on the way to the emergency room, I was holding her in my arms, and I thought that she was going to die. I mean, it was terrifying, actually, because I thought she was going to stop breathing. She was struggling to breathe. She was, I could still hear the way it sounds, it sounded on the ride to the ER. But I just thought she was just going to die right there in my arms. But what she was doing was hyperventilating, and her respiratory system was trying to get rid of as much CO2 as it could to lower to raise her blood pH because she was in acidosis. And that's what will happen. Thank goodness we got her there. Thank goodness she was a success story, and they got some insulin in her, and she was diagnosed, and she's been healthy ever since, except for the fact that she has to take insulin shots. But anyway, that's what was going on. The respiratory system will try to compensate when a person is in metabolic acidosis, which can come from diabetes. And this explains that. A rise in carbon dioxide will lower the pH, and that will cause the respiratory rate to increase. A drop in carbon dioxide will raise the pH, and that will cause the respiratory rate to decrease for the person to hypoventilate. Now, what will happen if the person is in acidosis or alkalosis due to respiratory reasons is that the kidneys, the renal system, will try to compensate for that and try to adjust the pH. The kidney tubules can reabsorb hydrogen ions at the level of the DCT and excrete bicarbonate ions when the pH is high, and that will lower the pH. And the kidney tubules can excrete hydrogen ions and reabsorb bicarbonate when the pH is low. So this is a chart that shows you all of the acid-base disorders, and I'm actually going to have to stop here with the lecture because we're just running out of time and just way too much material. But this is a very important chart. This is table 18-5, acid-base disorders. It gives you the disorder respiratory acidosis, for example. Says the pH is decreased below 7.35. It is the most common acid-base disorder, generally caused by hypoventilation and carbon dioxide buildup in tissues and blood. And the treatment is to improve ventilation, in some cases with dilating the bronchioles, bronchodilation, which you can do with medicine, and mechanical assistance. If a person has gone into metabolic acidosis, the same thing, decreased pH below 7.35. It is the second most common acid-base disorder, caused by buildup of metabolic acid, particularly ketones from diabetes, impaired hydrogen excretion at the kidneys, or bicarbonate loss in urine or feces. So they treat it by administering bicarbonate, and also in the case of diabetic ketoacidosis, by administering insulin. And respiratory alkalosis is when the pH is increased above 7.45. This is relatively uncommon, generally caused by hyperventilation. And the treatment is to reduce the respiratory rate. Somebody might hyperventilate because of the nerves. They may be having like a panic attack or something. So that would be an example. Now, metabolic alkalosis can be caused by prolonged vomiting, and it can be caused by dehydration. So the treatment is the administration of ammonium chloride is one of the ways you can treat it. Okay, so make sure you go through, this is table 18-5, and okay, how would a prolonged fast affect the body's pH? A prolonged fast affect the body's pH? Well, it's going to raise the body's pH and have the person go into alkalosis. All right, I'm going to stop here because there's really none of these questions on the exam, and we've gone way over the time.